My name is Matteo Repetto and I'm going to give you a brief overview of a GARD project. Today, most business processes follow a full digital workflow, including design, implementation, creation, purchase, production, trading, delivery, and after-sales services. Novel digital products and services emerge in business ecosystems with unprecedented rate with respect to the past, making monolithic ICT systems unsuitable to follow the market dynamics. The digital economy is therefore rewriting the rules of business and creating new models where services from multiple vendors are connected together to create, process, share, and distribute data and content. The ICT industry is already tackling the new challenges by introducing new architectures and patterns that bring more agility in the creation and management of new services and products, based on the provisioning of basic digital services that can be easily combined together to create more complex business chains. An example can be given for the automotive domain. A cooperative driving system may be designed by collecting information from vehicles through roadside units operated by traffic service providers, then delivered over a 5G network slice, and finally processed by a cooperative driving application deployed in the cloud. In addition, data from other subsystems like cameras and weather forecasts can be available from other cloud services. The composition of applications, cloud services, network slices, and smart things into service-oriented architectures or service meshes obsoletes the traditional security perimeter model. Specific security concerns in these scenarios include the need for more automation in security processes, so to avoid human errors in design, implementation, configuration, and management. The difficulty to guarantee the integrity and trustworthiness of a whole chain, since a vulnerability or a breach in the weak link of a chain can become a privileged attack vector to reach other services and processes. It is not coincidence that small devices and smart things are ever more preferred targets for initiating more complex attacks. The presence of unknown topologies at design time and the difficult to follow the dynamics of fully automated software and environments that evolve and morph during runtime. This raises questions about the overall behavior of the system, the location of personal and sensitive data, the sanity of the software, the availability of the whole service, and most of all, the ability to perform quick remediation and mitigation actions in case something goes wrong. The two main dimensions in a business chain, which are services and data, are directly reflected in the same number of security aspects: service integrity and data sovereignty. As a matter of fact, when connecting to an external service, be it a public sensor, industrial process, financial information, or customer database, the matter is not only if we trust its provider, but also how to detect attacks on that component and avoid their propagation along the chain. Therefore, on the one hand, there is the need to know who, how, and where will process private data and sensitive information, while on the other hand, there is the need to timely detect any attack or threat that may compromise the integrity, confidentiality, or availability of data and processes. The main challenges to be addressed by next-generation cybersecurity frameworks can be briefly summarized as follows. First, to include the security capabilities in the design and description of digital services so that they can be dynamically discovered and composed at runtime in a similar way to what happens for the main business logic. Second, to make the system programmable so that new security processes may be defined at runtime based on evolving attack patterns and new service releases. Improving the identification of zero-day attacks and sharing new findings are especially important to increase the robustness of the whole society. Third, to improve the visibility of cloud-native applications and services, leveraging effective and efficient technologies for monitoring and tracing different subsystems, the software, the network, the infrastructure. Finally, to create awareness and to facilitate response and mitigation actions by leveraging more integration with external CERT and exists and by introducing more automation to react to common attacks. The GARD project designs and implements a programmable platform to create custom security processing pipelines. The GARD platform mediates between monitoring and inspection tasks in digital services and detection for analytics algorithms by giving the latter programmatic visibility over the evolving context. The platform also includes information sharing as an effective means to propagate knowledge about the latest threats and attacks. From a more commercial perspective, the GAR platform improves current design and operation of security information and event management frameworks by explicitly addressing new computing paradigms beyond plain metal servers and new business models based on externalization and dynamic service composition. The vision of GARD is a multi-layer framework that distills trust, privacy, and security properties from a large set of data, like application logs, security events, packet inspection, network statistics, presence of private and sensitive data, security configurations, etc., providing tailored messages to different stakeholders, for instance, technical, legal, and management staff, final users. The unique characteristics of GARD will be programmability, which means the type, granularity, and amount of data to be collected will be tuned according to the specific needs, so to effectively balance precision with overhead. While recognizing the objective difficulty in applying legacy security paradigms for multi-domain business chains deployed over open and public execution environments, GARD leverages standardized APIs and interfaces to build an open cybersecurity framework. Just like an operating system exposes computational data and communication resources to applications via an API, so future digital services will include APIs that expose security properties, including configurations, monitoring, inspection, and enforcement rules. There are three main interfaces which are expected to collect data from local agents, to expose the capability of such agents and collect data, and to deliver notifications to humans and internal control processes. This approach facilitates the combination of different monitoring agents, data collection and delivery technologies, and multiple complementary detection algorithms and analytics engines. The platform does not implement any specific detection process per se, but provides all technical and management hooks to create security processing pipelines tailored to specific environments and operating conditions. The GAR project already delivered its preliminary software architecture, which is largely based on the Elastic Stack and the T-Rules business rules management system. The project is currently designing and implementing a set of complementary programmable agents that cover most monitoring and tracing needs, leveraging existing tools and the Linux kernel eBPF framework. A set of innovative algorithms will be designed for detection of known and zero-day attacks, risk analysis and penetration testing, data tracing. GUARD works in close collaboration with the Astrid project. For more information, please contact the project and technical coordinators or our communication manager. GUARD is also present on the web and main social media. Thank you for your attention.